So maybe I'll start, Vivek. So I'd
Yes.
rather highlight yours more. So I guess some people may trickle in still. So first, I mean, a couple people are taking this for a grade. This class, if you're attending, especially asking questions, then great, you're going to get A in this class. So the other thing is the VIS conference this year. So the biggest visualization conference, lots of stuff going on. It's often pretty expensive to attend, but this year it's hosted by the University of Utah. We've got a big VIS group. If you don't know, we've done it every 10 years, and it's going to be free this year. We sent something to the mailing list. So if you haven't seen already, but you're encouraged to attend. VIS is an integral part of the data science kind of spectrum, and so you might find some really interesting talks. So and with VIS, sometimes these are a bit more accessible at all levels, but it also gets kind of very you can geek out in that area as well. So please look into that. It'd be a cool experience to see that this year and get great representation from Utah. We'll probably say a bit more as it gets closer to the date.
Okay. So I have one more announcement. So this already Professor Jeff has said, and this is something I made in the morning. You can look at it. You can see www.ieee.vis.org for registration. And it is hosted by School of Computing, our professor. So definitely register and attend, like has Professor Jeff said. And one more thing is there's a social today. If you just want to have some fun for hour or I don't know 40 minutes something, we are playing Scribble. We will have customized the Scribble for data science words and all, so you can come enjoy. And obviously, if you haven't seen our club, please look at it. There is a Discord server, you can look at it. And now I think the seminar schedule is almost done. Every talk, most of the talk, what they are speaking and who are speaking is up on the calendar, so you can look at it. So I think that's all from my side. And let me stop sharing my screen where I can. Yeah, and now Vishnu can share the screen and I can.
Yeah. So as he's getting as he's getting his screen sharing set up, let me give a quick introduction. So Vishnu is speaking to us from my home state of Wisconsin, I think. So where he's a fourth-year PhD student at the University of Wisconsin-Madison, and so and he's currently also or possibly he's at Microsoft someplace. But so he's currently interning at Microsoft Research as well, and he's worked on a bunch of problems that at the intersection of fairness and machine learning, and today he's going to be talking about those problems applied to computer vision models. So great. So I'll look forward to hearing the talk.
Thank you. Thanks a lot, Jeff, for the introduction. I hope you guys are able to see my screen now.
Yes.
Okay, fine, great. So today we'll be discussing about some of the methods, specifically like optimization methods for imposing fairness in computer vision models. We'll begin with a brief survey of the field, and then I'll move into presenting one of our recent research in this area. Yeah, let me begin with this article that was published in the New York Times. This was published just a couple of months ago in the month of June. The article is about Robert Williams, a normal person. One day he just gets a call from the police asking him to appear in front of the police department to get arrested. Robert thinks that it's a prank call and he just ignores the call. Later in the day, the cops come in front of his home and arrest him, and in front of his wife and children. Apparently, there was a bug in the facial recognition system. Robert was wrongly flagged by this facial recognition system, and because of which he had to spend an entire night in jail. So this tells us that, you know, we have to be careful when deploying these facial recognition systems in practice. We should also be aware of something known as automation bias. Automation bias is basically we over rely on the correctness of these prediction systems and ignore any contradictory contradictory results. We just over rely on these prediction systems, and because of which, you know, because of which we can because of the errors made by these visual recognition systems, we can face some wrong consequences, just like Robert. So yeah, so within the computer vision field, one of the main problems is the lack of diversity in the data sets. Lack of diversity in the data sets is along, you know, multiple dimensions. For example, here it's in terms of the race. There is a lack of racial diversity in the data set. In this paper by Timid Jebru, she talks about some of these popular data sets where most like 80 to 90% of the faces were that of the people of a lighter skin tone. There is like serious imbalance in these data sets, and later she proposes a new data set PPB, which is more balanced, more gender balanced. Because of these highly imbalanced data set, facial recognition systems tend to perform very poorly, especially on darker skinned females. We need to be aware of these problems and develop solutions in this direction. Another dimension in which there is a lack of diversity is geographic diversity. Over here, DeVries et al. Show that the density maps of the objects in popular vision data sets such as ImageNet is different from that of the world population. On the left of the screen, we have the distribution of the objects in the ImageNet dataset, and on the right, we have that of the world population. There is, as you can see, there is a serious disparity between the distributions of these images. As a consequence, again in the same paper, as a consequence, in the same paper, they show that common household objects from lower income countries, which are underrepresented in these data sets, are often misclassified. For example, here in the leftmost column, we have the images of the soap. The first image is that of soap from the country Nepal, which is misclassified as food. And in the same column, you can see in the bottom, we have the soap, which is rightly classified from a country of origin like UK. In the middle column, we have spices from a country, the image of spices from a country like Philippines, which is misclassified as beer. And again, in the same column, in the bottom image, we have spices from USA, which is rightly classified. Again, the same situation for the last column, toothpaste. So here we see that, you know, these very common household objects, just because they are not represented well enough in the original data set, often lead to errors, often lead to misclassification. Right. So as a solution for this, there are like many couple of strategies to resolve or solve the fairness issues in a machine learning pipeline. We can classify these strategies mainly as pre-processing methods or on in-processing methods and post-processing methods. Pre-processing methods work and at the level of the data sets. We change the data set, we edit the data set, we either augment the data set or edit individual images to make the data set more fair or to restore balance in the data sets. That's where pre-processing methods work. Coming next to the in-processing methods. In processing methods, they typically accept a given data set and make algorithmic interventions to generate a fair model. Again, and a third category of methods are these post-processing methods, which take a pre-trained model and just adjust these decision boundaries on these from these pre-trained models. Among all of these methods, the post-processing methods are the fastest. However, you can see that the search space of a post-processing method is usually limited. You just have to shift the given decision boundary, because of which these fairness is not always guaranteed in post-processing method. Even if fairness is guaranteed, it comes at the cost of increased test set errors or bad test set accuracies. So yeah, so that's about post-processing methods. In this work, we will focus on some of the in-processing methods that make changes in the algorithm and just pick up any given data set, just change the algorithm and return a model that is more fair. In computer vision specifically, there is a great surge in a class of methods called as these adversarial methods. Adversarial methods basically try to generate latent features which do not leak any sensitive information. In adversarial methods, you have to train a discriminator model. You have an additional discriminator model, discriminator module, discriminator neural network, whose job is to hide or prevent the leak of sensitive information from these latent features. These are one of the effective methods. However, training these adversarial methods involves architectural changes, and they have complicated training routines because of discriminator and a generator. There's a game between discriminator and the generator, so convergence is not always guaranteed. So now we will move on to one of my recent works called as FairALM. This work was developed in an effort to provide a simpler alternative to adversarial methods. This work is a joint work with my co-authors Aditya, Satya, and Vikas at UW-Madison. Our objective was to frame fairness in computer vision as a constrained optimization problem and use tools from optimization literature to solve this problem of fairness specifically for visual data sets. Right. Yeah. So now we'll get into more of the FairALM algorithm. How was the objective? Was the problem formulation? How do we derive the algorithm for linear classifiers? How do we derive the algorithm for deeper networks? And we'll then see some of the experimental results. Right. So as you guys know, the primary objective in the machine learning pipeline is to minimize the test set errors. A couple of notations first. Let's see a couple of notations here. We have X as the features, or the X could be like some images in our visual data set. Y is the label. It could be like a binary label, or it could be like a multi-valued label associated with the data set. S is the sensitive attribute. For example, female or non-female, or it could be different race categories. So S is the sensitive attribute. H is our favorite classifier. It could be like a deep neural network or an SVM-based classifier, any of our favorite classifiers. And our goal here in the machine learning pipeline, in the data science pipeline, is to minimize the test set errors. Meaning that what we want to, our error could be quantified as the average of the misclassification rate, the number of times our model prediction H of X, our model prediction H of X doesn't match the actual label Y of X. So basically we want to minimize this, the expected average of the expected error, expected risk of these misclassification rates, misclassification between our model predictions H of X and the actual label Y of X. Right. So then that was our primary key objective in a typical machine learning pipeline. And we want to add this fairness as a constraint on top of this, our primary objective. Here we say that, you know, fairness can be treated as a constraint, as an equality constraint between conditional errors or conditional means. Let's look at the first measure here, the demographic parity. It is defined as the error conditioned on the sensitive group S. Basically, it is saying that, so when equating this demographic parity between group S0 and S1, all we are saying is that the errors made within the group S0 has to be same as the errors made in group S1. So that's the typical intuitive notion of fairness. The errors made in, say, the female group has to be same as the errors made in the non-female group. That's our demographic parity measure, which can be seen as an equality constraint between these two errors. While demographic parity is a good measure, let's think of a situation where, say, we have to predict heart failures from individuals. So it is known that heart failure is more common in men than women. So there is a positive correlation between gender and the condition of heart failure. So in those cases, you know, whenever there is actually a good correlation between the sensitive attribute and your target label, demographic parity may not serve as a good measure. In this point of view, like fairness literature has suggested alternative fairness measures such as equality of opportunity and predictive parity. If you look at equality of opportunity, the conditional error is, the error is again conditioned on the sensitive attribute and also the label Y is equals to 1. Essentially, we are saying that we want to match the errors between the two groups S0 and S1, but only among the positive labeled samples. So that is the notion of equality of opportunity measure. And like there are some other measures like predictive parity, which also work in the similar spirit. The underlying message here is that any given fairness measure can be treated as a equality constraint and it can be added onto our objective function into our optimization problem. So basically, this is our constraint optimization problem. We want to minimize the test set errors E such that the errors, again, here we are using the demographic parity. Again, we can extend it to other fairness measures as well. But our goal is to minimize the test set errors such that the errors made in group S0 is same as the errors made in group S1. Recall that H is our classifier. H could be like the weights of the deep network that we want to optimize for. H is like the best network that we want to choose. We want to search in the space of the weights of the network such that, you know, our test set error is minimized and the errors that we make in group S0 is same as the errors that we make in group S1. Again, here we are considering only two sensitive attributes, S0 and S1, like for example, female or non-female. We could extend this to multi-valued sensitive attributes as well, which would just result in adding more constraints into this optimization problem. Right. So having looked at this optimization problem, we will now write down a Lagrangian function for this. So Lagrangian function just would bring the constraint into the objective. So here we have introduced a new variable lambda, and our Lagrangian formulation now includes the error EH for a classifier H, and it would also include the difference, the lambda times the difference of the errors among in the group S0 and S1. So now, using this Lagrangian formulation, we will solve a dual problem here. We will write this as max over lambda and min over h, L of h comma lambda. Lambda is the dual variable that we have introduced that handles the equality constraint. So again, here we are solving the dual problem max over lambda and min over h because of computational reasons. Mainly it's solving a dual problem over the primal version. A primal version would be min over h and max over lambda. Dual version is max over lambda and min over h. We solve the dual problem because it's often easier to append more constraints into the dual problem. And also, like, if you have like multiple constraints, solving a dual problem would mean transforming multiple constraint into a multiple variable problem, which is often more easier. Also, solving a dual problem, we can exploit some problem-specific characteristics and provide more efficient solutions when solving the dual problem. One point to note here is that the inner minimization problem here is non-smooth. Non-smooth meaning that the gradients keep varying very frequently. So because of this, the gradient-based methods such as SGD may not work well, and especially like in higher dimensions, gradient-based methods tend to fail if our objective is non-smooth. As a solution to this, to resolve.
So I think I can ask you a question before you move on.
Sure.
So have you explained how you measure the difference between the two distributions, mu S0 and mu S1, and maybe you said it quickly and I missed it, but I'm just curious about that.
Sorry, curious about what?
So you have this in your optimization is right. You have mu of H sub H of S0 and mu of sub H of S1, and so is this is mu just a scalar value, or is that representing the whole the whole distribution of that trait? I guess that part of your formulation I was confused by.
Mu is actually a scalar value. That's a good point. Mu is not a distribution; it's a scalar value. Basically, it's the error conditioned on the sensitive group. So roughly saying, what's the error in group S0?
Oh, okay.
And what's the error in group S1? So it would have the same formulation as this EH expected error, but there would be a conditioning over here, EH conditioned on group S0 or group S1. Basically, the misclassification rate within the female group or the male group is just a scalar value. Yeah. If you have more,
so then do you want an absolute value there, or is it? Do you have a preference, like on your next slide in the?
Right.
Or yeah. So do you want absolute value on the difference then?
Absolute value is not required actually, because we just maximize over lambda. If we have an absolute value, then we would have to put an additional constraint that lambda has to be either greater than 0 or less than 0. Here, absolute value is not required.
But then you could have a big difference in, like, in one direction. So you could make, oh, because they both affect the overall error rate, EH, right? But you could have that the, if you wanted to minimize this, you could have that the error rate for S1 is very large. And that would make this, potentially make this whole equation smaller.
So when the error, here when solving this problem, max over lambda, if there is any difference between the error rates, then lambda basically goes to, chooses a lambda would be chosen, some value of lambda would be chosen such that the overall objective would become infinity. In either direction, say if mu s0 minus mu s1 is, say, some positive quantity, then lambda would be chosen as a positive infinite value such that the entire objective will become positive infinity. In the same way, if mu s0 minus mu s1 is, say, negative, say -3 or something, then lambda would be chosen as minus infinity such that, entire objective will again become infinity. So this objective will be feasible only if the constraint is satisfied. Mu s0 minus mu s1 becomes 0. So imagine this having a so just imagine that the inner minimization problem is already solved. So we have, for some h star, we are looking at this objective EH plus lambda times S0 mu S0 minus mu S1. If the constraint is not satisfied, if mu S0 minus mu S1 is, say, a small positive quantity, or if mu S0 minus mu S1 is a negative quantity, in either direction, max over lambda would just be infinity. So the Lagrangian, our solution would just become an infeasible value. Our solution would be possible, our objective would be feasible only when the constraint is satisfied. Okay, over here, yeah.
Sure. Okay.
Yeah. Right. Cool. So, right. Now coming to our, so in order to handle the non-smoothness, we will add a proximal term over here, lambda minus lambda t squared, into our Lagrangian formulation. So this lambda minus lambda t squared acts as a regularizer. It just improves the convexity of the inner minimization problem. So now, since we have added lambda minus lambda t, our Lagrangian formulation is also a function of lambda t. Lambda t is like a fixed constant, and the only variable here is lambda. So now let's look at this. Having looked at the Lagrangian formulation, let's derive an algorithm for solving max over lambda and min over h for linear classifiers. So here we consider, a linear classifier. So we will imagine that we have n trained classifiers. We already have n different trained classifiers, and we also know the errors of these individual n trained classifiers. Our only objective here is to find a good linear combination of these n trained classifiers that is fair. We want to find a good linear combination of these n classifiers that not only minimizes the test error, but is also fair. So this setup is again inspired from Agarwal et al. In their reductions to fair classification paper. So now note that, since our goal in linear classifier setting is to choose a linear combination of n given classifiers, we can reformulate our Lagrangian something like this. So we will introduce Q as our selector variable. It is it is any value between 0 to 1, and it is a vector of n dimensions. So our Lagrangian would be reformulated as an inner product between the Q vector and these errors of each of the each of these n errors. Similarly, for the conditional difference, conditional error terms of mu h s0 minus mu h s1. So now again, our goal is to maximize lambda and minimize Q for this Lagrangian formulation. So first we have to solve the inner minimization over Q. Observe that the Lagrangian formulation is linear in Q. So solving the inner minimization would just imply solving a linear program in Q. It will also imply selecting, since Q forms a simplex, it will just imply that we have to select one of these n classifiers, one of these n best classifiers. Now, after solving this min over Q, using this argmin, with this linear program, we will move to max over lambda. In order to solve max over lambda, we maximize the total cumulative regret, and then we get an update like this for lambda. So this way, like, we solve the inner Q and the max lambda, and we get different update step for the Q variable and for the lambda variable. Right. And then, like, in our work, we show that following this update for the Q variable and following this update for the lambda variable, after T such updates, we hit upon a saddle point. We hit upon actually an approximate saddle point. Basically, we say that with respect to the best solution, we are in a window of size mu compared to the best solution. Yeah, so here all these this basically means that with respect to best solution, we are in an approximate window of size nu. Yeah, size nu. So again, we calculate what is the width of nu, what is the size of this window, and we show that there is a minor improvement with respect to what was reported in Agarwal et al. Now coming to our more interesting setting of deep neural networks. The previous setting was simply like a linear classifier, and it was more of a post-processing step. We have already n trained classifiers. How do we get a good linear combination between n trained classifiers? Now we have deep neural networks which are actually used in vision settings. So how do we solve the Lagrangian? How do we solve the max over lambda min over h for these deep neural networks? So one change is that one adjustment that we need to make is that the errors is basically an average over the average over the errors made over all the samples. So this error contains an indicator function. This contains the hard indicator function 1. We have to replace this indicator function with a smooth surrogate such as a logistic function. Main reason is that this indicator function is non-differentiable. So if we take gradient, it is either mostly 0 when like x is h of x when h of x not equal to y of x is less than 0. It is mostly, the gradient is mostly 0 in its domain. So in order to use gradient-based methods such as stochastic gradient, SGD, we have to replace this hard indicator function with a smooth surrogate. Similarly, again, the errors and the conditional mean terms were we cannot calculate the exact distribution of these errors and the conditional means. So we will actually find an empirical estimate using a given training data set. So this is a common practice in like a machine learning pipeline. You just pick up a training data set, you train your model on this training data set, and then evaluate it on test data set. So on this training data set, we compute these errors, EH, and we compute these conditional errors among the groups S0 and S1 on this training data set. So with these adjustments, there is one more thing is that, we have to solve max over lambda and min over h. H now becomes W because we want to optimize, we want to tune the weights of the neural network. So recall that in the linear classifier setting, the min over h or min over W was a linear program. So we could easily solve the inner minimization problem because it had a closed form solution. However, for deep neural networks, solving min over W it's not possible. Because of the non-convex objective. We may need to run multiple steps of gradient descent to minimize W. So in order to attack that, we try to find an upper bound on these Lagrangian objective. We basically, by interchanging the min and max, we find an upper bound to our original Lagrangian objective. If you look at the second equation, the inner max over lambda is now a quadratic function over lambda. So the inner max over lambda can be easily solved to get an update rule for lambda. We have a closed form solution for lambda. So that basically becomes the dual update. And then substituting that lambda into our objective will give our final FairALM objective. Note that we have reduced the max min formulation into a single minimization problem in the last inequality. The single minimization is over W. And now we can run like multiple iterations or multiple steps of gradient descent in order to optimize this. So let's look at like what is our main algorithm. How did we when moving from the Lagrangian formulation to the actual algorithm, what steps have we need to take? What steps we need to take in actually running this algorithm? First is that we have to sample some data, a small subset of data from our training data set. Let's call that Z. Then we will compute our FairALM objective, which contains the error on the training data set and the the conditional error terms in the group S0 and the group S1. We then pick up a subgradient nu t on this FairALM objective. We update the weights of the neural network using the subgradient nu t, and we update the lambda variable, the dual variable lambda, using this dual update step. Let's contrast this with an unconstrained model. A typical neural network training on the left here, the typical neural network training procedure would involve sampling data Z, computing the training loss, and then doing a weight update on the training loss. In a fair algorithm, all we need to do is we again sample Z. We sample a small subset from the training data set. We compute the training loss, and in addition to the training loss, we also compute the loss among the groups S0 and S1, and then add a weighted combination of S0 and S1 into our entire loss function. The weights here are a function of lambda. So we also provide in step 6, we provide a way to update the coefficients of these difference of conditional errors in the FairALM objective. Step 5 would be the same as in an unconstrained case. It's basically a neural network weight update using the subgradient on the loss function. Now we will take a look at some of these experimental results. So basically we have, just as a recap, we framed fairness as a constrained optimization problem. We wrote down a Lagrangian function for it. We solved the dual variant of the Lagrangian function. In the dual variant, we saw that the inner minimization was non-smooth. So in order to, as a remedy for that, we add a proximal regularizer term into the objective. We derived we solved the max over lambda min over h for a linear classifier, which gave us a update for lambda, h and lambda for the linear classifier setting. For the deep neural network setting, we again found an approximate upper bound to our FairALM objective, and later we show that we told that we'll use SGD to optimize the weights of these deep neural network on this newer objective function. The weights in this objective function, the weighted difference of the conditional errors, are again updated by the dual parameter lambda. Coming to some of these experimental results, we here again we pick up a standard data set called as CELEBA data set, which is a faces of which contains the faces of many celebrities. We plot on the y-axis, we plot the fairness measure DEO, which stands for the difference of equality of opportunity. Basically, lower fairness measure would mean that the model is more fair. Higher DEO would imply the model is unfair. We plot the DEO measure during the course of training. Here we observe that, you know, naively penalizing for the fairness measure is usually very unstable. The DEO measure fluctuates a lot, as shown in the red curve here. In contrast, a fair, using the help of the proximal term, a fair model is more stable. The DEO measure is doesn't fluctuate a lot, as shown by the blue curve here. Similarly, in the same data set, we try to predict different labels present in the data set, such as attractiveness, bangs, or high cheekbones, mouth open, smiling, etc. So here again, we plot on the y-axis, we plot the DEO fairness measure, difference of equality of opportunity. And we find that the red points, which correspond to the unconstrained model, have a higher DEO measure, meaning that they are more unfair, meaning that the errors made in the male group and the female group are different. Whereas a fair model would make the same number of errors within the male group and the female group. So that is for, again, male versus female. On the right of the screen, we have young versus old. Here, the sensitive attribute is age. Basically, we just want to make the same number of errors in the young group and in the old group. A naive, unconstrained algorithm would make different errors in the young group and the old group for the labels such as attractiveness, male, cheekbones, etc. Whereas a fair model would make equal number of errors in both these groups. In both these examples, the test set errors do suffer, but they do not suffer a lot. They suffer just in the window of 5%. So at a cost of 5% of test set error, we are improving the fairness measure. We are improving the fairness of the model, meaning that the errors made in both the groups, in either male or female or young or old, would be same. Right. Now, using the most unfair label in the previous example, which was attractiveness, and for the protected variable gender, we try to plot the heat maps or these activation maps on these images. Basically, these activation maps inform us where the neural network is focusing on when making its prediction. Which of the regions in the face is the neural network paying attention to when it makes a positive prediction. Here, if you see an unconstrained model, the middle columns here, middle column, the neural network focuses on the entire region of the image to make its prediction. Here again, in these examples, we want to predict whether we want to predict the label attractiveness in these images. Each image has a label associated with it, which says whether the image is attractive or not attractive. We only want to predict that label, attractive or not attractive, available in the CELEBA dataset. Right. So now with this, and basically just as a disclaimer, we don't want to say we don't want to make a general purpose classifier that given an image that classifies its that claims the image is attractive or not. We don't want to do that. We only want to predict the label that is available in the CELEBA dataset, which stands for attractiveness or non-attractive. These images were labeled by some crowdsourced labelers. So essentially, we are trying to predict their decision for attractiveness or non-attractiveness. In all these images, if you see an unconstrained model, when predicting for the label attractiveness, looks at entire region of the face. It uses the entire face region to make its prediction. And for this reason, what happens is whenever you get an image of a woman, it automatically classifies it as attractive because the original data set, there were more female images that were labeled attractive. In contrast, a fair model, the rightmost in these examples, the fair model only focuses on some specific regions of the face in order to predict the label attractiveness. As you can see, like in all these fair models, the region that the neural network is focusing on is a small region. It is mostly towards the right of the images, right side of these images. The right side of this image corresponds to the left side of the face. So basically, a fair model is focusing on the left side of the face in order to predict whether the image is attractive or not. Like we were surprised why the model was focusing mostly on the left side of this face. Apparently, like there are many psychological studies that say that if you just do a quick Google search over here, if you just do a quick Google search on which side of the face is more attractive, you'll just get that it's left side of the face that usually people use the features of the left side of the face to classify someone as attractive or not. This was a positive sign for us, indicating that the original labeler, so our neural network is trying to predict the decision made by the original crowdsourced labelers. And it says that, you know, even the original crowdsourced labelers happen to focus more on the left side of the face in order to classify an image as attractive or not. This was about these CELEBA data sets. Now, in another data set called as IMSITU data set, we look at a different experiment. Basically, in this IMSITU data set, we have an image and we have an action or a verb associated with an image. For example, in these two images, which are basically the same image, we have a label cooking associated with these both of these images. Our task here is to predict, use a neural network and to predict whether the image represents the verb cooking or not, whether the image represents the action cooking or not. Again, here we compare the activation maps of an unconstrained model and a fair model. Basically, comparing the activation maps, we see that, you know, in an unconstrained neural network, the neural network is focusing on the person is focusing on this specific small region of the image, the person region of the image, in order to classify it as cooking. Whereas a fair model is focusing on the food, which is more aligned with our target label cooking in order to predict the label cooking. So again, it can be thought of like one can find that an unconstrained model focusing on the person leaks the person feature often leaks the gender information. So an unconstrained model often might use the sensitive information present in the image to make its decision. Whereas the fair model is, since it's focusing on non-gender revealing feature of the image, it successfully conceals the sensitive gender information in this during model prediction. Here we have another example. Here we want to predict the verb microwaving, which is again associated with both these images. In an unconstrained model, the neural network is focusing on the face and like utensils also to predict, to classify this image as microwaving. We know that face is leaks the gender information, whereas the fair model here is avoiding the face region. It's focusing more on the microwave and utensils to classify the image as microwaving. Here are some other examples. Again, here we have cooking. An unconstrained model focuses on gender leaking features such as person. Fair model focuses on non-gender leaking feature, gender concealing features such as food. This is driving versus, again, we want to predict driving here, the verb driving. An unconstrained model focuses on hair, which is related to gender, whereas a fair model focuses on the steering wheel, which is more associated with the verb driving. Here we want to predict the action shaving. An unconstrained model is looking at nail polish, which is related to gender. Fair model is looking at razor, which is more non-gender revealing.
Vishnu,
yeah.
We have a question. Aishwarya, can you ask?
Yeah, hi, Vishnu, I just wanted to ask you one question. So as we are taking into account the difference between the mean for the two samples, right? One with the sensitive attribute female and the other one not female. So how does this work for unbalanced data set? So let's say I have a data set in which there are 80% data for females and 20% data for males. Then how does it work, like this metric, the difference between the means?
So even in the unbalanced data set, among the 80, so let's say we have only 100 samples, we find the error in the 80 group. We get some measure of error in the 80 group, 80 male group. And we get some measure of average error made in the female 20 group. And our difference of this errors between the male and female group is our fairness measure. We want to minimize the average error made in the female group and the male group. So simply saying, even in the unbalanced data set, we will be using the same metric. We don't rely on the balance of data set in order to compute this fairness measure.
No, that I got it, but I just wanted to ask whether you have tested it for unbalanced as well. Like, was it performing good?
Like, in all these examples are for unbalanced data sets only. So in each of these cases, one key reason why the unconstrained model is performing bad is because of the imbalance in the data set. In all these examples, like we have, in any of these examples, cooking is often more associated with the verb woman than man. So I think even this was around 3:1 ratio for cooking and female and cooking and male. So because of this imbalanced data set, because of the key reason being of the imbalance of the data set, the unconstrained model is making these errors or looking at incorrect features in order to make the prediction.
Okay, and also one more question. So when you talked about linear classifiers, you used an ensemble for which you learned a vector Q. Did you do the same thing with deep networks?
Sorry, what?
So when you were talking about linear classifiers, there was a vector Q. which was basically the combination of multiple classifiers which you have learned. So are we using the same ensembles in deep networks as well?
Oh, no. In deep networks, we do not use an ensembles. We use, we have only one given neural network, and we use SGD to update the weights of the neural network.
Okay.
Yeah.
Thanks.
Sure. So yeah, again, coming to these examples, yeah, this is the last example. Here we want to predict the verb assembling. In this case, simply, you know, both the unconstrained model and the fair model are looking at the right regions, the helmet, but the fair model is looking at is looking at helmet and tools, which is more aligned, which is a little bit more aligned to the target label assembling than the unconstrained model. So finally, like, where else can we use fairness?
Vishnu, there is one more question if you
sure.
want to take. Okay. So are there issues that arise from trying to enforce fairness on a model trained on a biased incomplete data set that would be absent with a more fair complete data set? It seems like in-processing strategy may be effective but don't address the root problem. So this is by Alex. So yeah.
So what is the question here?
Can you go, Alex? Can you unmute and clear it out more? Alex?
Hello.
Yeah. Go ahead.
Can you hear me?
Yeah,
okay.
Yeah, we can hear you.
Yeah, I was just wondering, like you mentioned, maybe a slight decrease in test set accuracy for the FAIR model. I was wondering if there are potentially any other issues that arise from trying to enforce fairness on a data set that may not really be representative of the population, or the data itself maybe you could consider to be unfair. So it seems like we're kind of patching over the issue, and maybe it's working really well, but it, at least just to me, it seemed like ideally we would have, you know, a perfectly fair data set. And so I was just wondering kind of if you knew of any differences between, you know, the in-processing method that we're using here versus, you know, having a more complete data set.
Usually it is very difficult to find a more complete data set in practice. Even like if we balance for gender, even if we balance for male and female, a network could often use some surrogate feature in order to make its prediction. So let me give an example. This was again an example from a paper called Balanced Datasets Are Not Enough, which basically says that even if we balance for male and female for the cooking verb, a deep neural network might choose children as an object to make its prediction. It uses a surrogate feature such as children to classify the verb cooking. So that's one of the drawbacks of pre-processing methods, that even if we strive to balance the data set in a very perfect manner, the neural network can still look at incorrect features to make its prediction. Main reason being that these vision data sets are not very well diverse. So for a particular class, we may have only fewer samples, and the model might just overfit on those fewer samples. It might just use incorrect features from those fewer samples to make its prediction. So that's one of these drawbacks of pre-processing methods.
Okay, great. Thank you.
Yeah, cool. So right now, finally, like beyond fairness, where else can we use fairness-based research? So this is one example where we have to pool data sets from multiple sites. Here we are looking at the chest X-ray images from one hospital, Shenzhen, and another hospital in Montgomery. In these cases, usually, like especially in these biomedical applications, the training data sets are very few in number. So there is a necessity to pool data sets collected from multiple different sites. But as a consequence of pooling data sets from multiple different sites, we often introduce some site-specific artifacts into the data set, such as these site-specific artifacts are marked in red over here. Because of these site-specific artifacts, deep neural network might use these site-specific artifacts while making its prediction, rather than actually looking at the image of the chest X-ray to make its prediction. So in a way, here the fairness problem is to make the predictions of the neural network fair with respect to the two hospitals, Shenzhen S0 and Montgomery S1. In another example here, again within the category of multi-site pooling, here we want to predict the status of Alzheimer's disease in based on the brain images. Based on the brain image scans, we want to predict the status of the Alzheimer's disease. Usually, like, you know, these brain images are collected from different scanners, such as GE or Siemens. Collecting it from different scanners often can introduce a scanner-specific artifacts into the images. These scanner-specific artifacts can be shown, can be seen in this red circle over here. There is a slight difference in these. It's basically the same person, but there's a slight difference in the scan obtained from a GE machine and a Siemens machine. Because of these scanner specific artifacts, a neural network can rely on these scanner specific artifacts in order to make its prediction, rather than actually disease specific regions in an image. So fairness objective here would be to make the predictions of a neural network fair across different scanners, GE versus Siemens over here. So these are like some of the places where one could use fairness-based methods outside of, you know, sensitive attributes such as gender or race. So I guess, yes, I think that was my last slide. And if you guys have any questions, I'm happy to take that.
I have a question.
Sure.
My question is about fairness. Like, is fairness even clearly defined?
That's a good question. Fairness is mostly like a social construct. What I consider fair might not be fair to some other individual. However, you know, as a step in direction to, you know, at least improve fairness, we can rely on some fairness measures, some fairness objectives, and try to see whether those fairness objectives are met by existing deep neural networks.
Okay. But then, so there's really no way to like truly like create fairness then, right? Would you say?
Yeah, it's a very difficult problem. We need to involve research from the social side and mathematical side to actually address the question. Also, there is like many works that say that, you know, if you have like multiple fairness measures, one cannot satisfy all these fairness measures at the same time. So yeah, so that's still an open question to think about, whether the true goal of fairness can be achieved. But here within like fairness research, in computer vision, we set an objective. We state that this is our fairness measure, and we try to see whether our stated fairness measure is met during training or not.
Okay. All right. Thank you.
Yeah.
So for implementing approach that you recommend, rather than having like the researcher, the person using these types of approaches, like saying, oh, I have to correct for gender or race or something like that, can you simply just always apply this whenever there is a class that has a low population? And should we, you know, maybe start adopting this technique for classes that have low population representation?
Yes, yes, definitely. Like it's in situations where we know that there is a difference in the number of samples between the two groups, and we know that a model can suffer from this imbalance, we can definitely use fairness measure methods like FairALM, or simply penalizing the difference of the errors between the two groups will also be a good enough method.
Great. And one more question, kind of comment. Oftentimes it seems like the output of these neural network models, it's not really discussed or displayed to the user, the certainty, uncertainty of the model output. For example, you know, if it's a multi-class, it could be predicting many classes with a high probability, but one class has the highest probability, so it gets that predicted class. Do you think that could potentially solve some of these bias issues and trusting the network too much?
Yeah. So there is also a problem that predictions, especially ReLU-based networks, give overconfident predictions on, you know, even when the test data set is slightly different from the training data set, a good network has to reduce the confidence of prediction when the test set is different from the training set. However, like there is research that shows that ReLU-based networks give higher confidence predictions even when the test set is different from the training set. So research along that direction, basically using the confidence of the predictions, can, you know, inform us whether the neural network is tending towards making a correct prediction. So even like in simply saying that using confidence of the prediction as a metric to reduce bias is also a good strategy.
I have another question.
Yeah.
This is kind of a question I've wondered about. If you have like a one racial group or like just one particular group overrepresented in something, does that automatically indicate bias?
Like there is, it depends on how you, what do you mean by bias here? Here, if you mean that imbalance in the data set, then yes, in this data set, like one specific race group is number of samples from one specific race group is more. So there is a bias in terms of the balance in the data set. Yeah.
Okay. But then does that also indicate like some sort of that also would indicate like the system itself, like used to judge these people are biased? Is that what you're saying?
No, I wouldn't say anything about the system. I would just say that, you know, the data set is imbalanced. The data set, there is a bias in the balance of the data set.
Okay. And here's another question. This is kind of where it's leading up to. Have you heard of the statement where like people have argued that like Asian Americans are overrepresented in places like elite colleges or like in STEM everything? Do you personally think it's because of a racial bias?
So if you don't want to answer that question, that's probably okay too. That's
understand.
Yeah, that's.
I think we can avoid that question.
So if you want to say something, that's fine. But that's kind of a weird. I don't want to put you in an awkward, position on the spot.
Sure. Let's avoid the question.
Yeah.
Okay.
So there's one question I wanted to ask, maybe if, so you use gender as a category that was protected, but so gender is not actually binary. This raises so a few issues, and I think this challenges this especially like hard to abstract. We've do the same with like age, which is also not binary. Like, is there a way to do something similar with some scalar attributes, or a thing that at least has an ordering to it?
Right. Right. So in case of age, yeah. Right. That's actually a very good question. In case of age, the sensitive attribute is actually continuous. The way we can use the model that I just described is to discretize age, to bucket age into, say, 10 different buckets and ensure fairness across these 10 different buckets. It's still an active area of research how to actually, incorporate, a continuous sensitive attribute and impose a fairness with respect to a continuous sensitive attribute. Right.
So sure. So thanks. So we're getting pretty close to the end. If anyone has any more questions, so you can also ask them quickly. So if not, so then let's thank Vishnu one more time. So thanks for the great talk, the very interesting work, and the great discussion afterwards.
You can do the virtual clap if you want.
Yeah.
Cool, great, thanks. Thanks for inviting me. It was very fun to had a great time presenting my research and the brief survey. Happy to be associated with any of the future talks as well.
Okay, great.
Great. Thank you.
Thanks.
Thank you. Bye-bye.